Hi, welcome to AhaGuru question types for JEE and NEET. Every week I will take one important question type that appears in JEE and NEET. So we'll basically look at the physics papers, look at the previous year questions of one type, analyze how to solve that in detail. So by going through this video carefully, you will be able to understand how to solve such questions very quickly. Okay? So today we are going to focus on capacitor circuits with switches. Now this is important, with switches. Now often students know how to solve capacitor problems when the capacitor is connected to a battery. That's it, right? That kind of question is relatively straightforward. But when you have a capacitor circuit where you're going to switch from one position to another, then things change a little bit and often students get confused by such questions. But do these questions actually come up in JEE? Look here. Almost every couple of years you will get a question based on capacitor circuits with switches. Okay, this has appeared many times in the JEE. Okay, so look at this question that appeared in 2025. So you are basically connecting the C1 first to a battery, then you're removing the battery and then connecting it to C2 and then closing the switch. And the question that is asked is, after some time when equilibrium is reached, then what will be the charges on the two capacitors C1 and C2? Okay, so this was asked in 2025. 2019, a question was asked here where the switch is basically going to be turned from A to B. Okay, 2018, by the way, switch basically turning from A to B is actually exactly the same idea. You put a battery, you remove the battery, but that's exactly what you're doing when you're flipping the switch from A to B, right? Here it is connected to the battery, then it is connected to some other capacitance. So we're going to learn how to solve such problems. 2018, again you can see very similar kind of question has been asked, except instead of one capacitor, you have two capacitors in series. So we need to basically know how to combine them, that's all. And look at this one that appeared in 2022 in JEE. Again you can see very similar to the 2025 question. So basically we need to understand how to solve questions involving switches and capacitors. So let us learn this. Now these kinds of questions are going to be very important, and actually they are very easy. As you're going to see when I solve this, you will realize that these questions are very easy. Now if you want to learn more of these kinds of questions, please do hit the subscribe button, because that will ensure every week when I do this, you will get the notification. You will never miss any of these sessions. These are going to be super important for JEE and NEET. You're going to learn exactly how to solve this kind of a problem. So when you learn every type of problem that comes up for JEE and NEET, you will be able to do these problems in the exam without any difficulty. Okay, let us now figure out how to approach these kinds of questions. So let us start by first looking at the basics of capacitors that you of course know. If you take a capacitor with capacitance C, and let us say we apply a potential drop V. So the potential drop is this way. So this is at a higher potential, this is at a lower potential. I'll say that this is the plus, this is the minus. So that is at the higher potential, this is at the lower potential. Okay, so then this side will become positively charged, this will become negatively charged. So let us say that the charge is plus Q there. So obviously it is going to be minus Q here, right? It will be minus Q on this plate. So usually we only mention the plus Q. Automatically the other plate will be minus Q. Okay, so now what will be this Q? Q will be C into V. Q is equal to C into V. So that formula of course you know. And what will be the energy stored in the capacitor? Half CV square, or you can also write it as Q square by 2C. There's another way to write it, half Q into V. That also you can do. CV is Q. So half Q into V, I'm not writing that down. But Q square by 2C, half CV square, half Q into V. These are three different forms in which you can write the energy stored in the capacitor. Now this is basic stuff. This is something that you are supposed to know. The moment you learn about capacitors, you immediately learn both of these formulas. But how does that help us solve problems with switches? Let us try and understand. So let us take a situation like this. This capacitor C1 is connected to this battery in the beginning. And then what are you going to do? You're going to take the switch and you're going to move it there. But before that, right now it is connected to this battery. Well, this potential drop is E. So therefore the potential drop across C1 will be E. Right? And therefore the charge on this plate Let me call it capital Q. Capital Q. Okay, what will that be? CV, right? Here it is C1E. C1E. And what will be the charge on this? This is 0. It's not connected. But right now, this is the initial case, right? Initial situation. This is connected this way. C1 has a charge Q equal to C1E. Now suppose I take this switch and move it that way. It is now disconnected. This charge can't go anywhere. But I'm not going to stop there. I'm going to connect it to B. So let me show you what it will look like. So I'm going to flip it around like this. There was a charge Q. There was a charge Q here, right? But now, once you have connected, some of the charge is going to flow like this. So if I have a charge small q that flows here, what will happen to this charge? Will it still be capital Q? No, because charge is conserved. So this charge, if it goes that way, this is now going to become capital Q minus small q. Because small q is the amount of charge that is flowing that way. How much charge will flow? That's a good question to ask, right? How do we know that? Basically, you see this point and this point, they are connected. These 2 points are connected. So that means this potential drop and this potential drop, they must both be equal. So the main point is the potential drop across C1 must be equal to the potential drop across C2. Will it be equal to E? It was E here, right? Will it still be equal to E? No. When this is E, this charge is C1E. But now some of the charge is gone that way. Is it connected to the battery anymore? No. So now this charge has decreased. So this V is not going to be what it used to be. In fact, I can even calculate it. I can write V is Q minus Q by C1. C1 into V will be Q minus Q. So you can write it is Q minus Q by C1. But wait a minute. Can't I also write it as Q by C2? Yes. You can also write it as Q by C2. Notice this gives us an equation. Capital Q you already know, C1E. C1, C2 you know. So if you solve this, you can find what small q is. You can actually find out how much charge is going to flow. There are different ways of doing it. You can say, okay, these two are right now in parallel. So the net effective capacitance is capacitance in parallel. What is the formula? Resistors in series, R1 plus R2. Resistors in series formula and capacitance in parallel formula will match. So capacitors in parallel formula, C1 plus C2. Okay, so you can say effective capacitance is C1 plus C2 and the total charge on both the plates, how much is it? Q minus Q plus Q, which is capital Q, right? Please remember the charge gets split between C1 and C2, but the total charge has to remain the same. So you could use that. You can say capital Q. You can also write V is total charge, which is capital Q, divided by the total capacitance. What is the net capacitance? C1, C2 in parallel. Okay. Now you can say in parallel C1 plus C2. So C1 plus C2. You can also use this. If you solve this, you will find that that is what you're going to get for V. Okay. You can try that. This and this lead to the same thing. Okay. This is telling us this potential drop is equal to that potential drop, which of course is very important. And potential drop is charge divided by capacitance. Charge is C into V. So therefore V is equal to charge divided by capacitance. So that's what I've done. But this V is equal to that V. And so that is small q by C2, Q minus Q by C1. And so if you cross multiply, you will be able to quickly see that this must basically be equal to that. Right? You will get the same answer. Anyway, so we can use this to solve and find out what is V, but we can also use the fact that parallel capacitors, the net capacitance is C1 plus C2. So these kinds of ideas we are going to use, but what is the basic idea here? The charge that was there initially is going to flow, part of it is going to flow, then you have to ask what is conserved, what remains the same even if it is split? Charge. Charge is conserved, so the charge gets split. And then what will be the same? Finally, this potential drop and that potential drop has to be the same because they are connected there, connected here. So these two principles, right? we are going to use to solve a question like that. That you can convert into an equation like this, or if you like to use equivalent capacitance kind of formulas, then you can convert it into something like this and solve. So we are going to see how we can use these principles to solve the previous year questions from JEE. Let us now do that. Let us now see how to solve this question that appeared in JEE in 2025. A capacitor C1, 6 microfarad, is charged to a potential difference of 5 volts. So this is 5 volts. So that basically means once the switch is connected here, this will be 5 volts. This will be 5 volts, right? So that will mean that the charge on C1, okay, we will call this, let us say, capital Q. How much will it be? C1 into the potential drop. C1 is 6 microfarad. So 6 microfarad into 5 volts. 6 into 5, 30. 30 microcoulomb. 30 microcoulomb. So that will be the charge, right? So we basically connected it to the battery. Then what do? Then we disconnect. So basically we disconnect. So that means there is no more battery. And then battery is removed. And another capacitor C2 is inserted. So we take this out and we put a C2 like this. So at that point, this charge will be 30 microcoulomb. The same charge will be there. No, once you have disconnected, the charge can't go anywhere. And then what will happen? Once you have connected this, right? Nothing will happen because the switch is still kept open. When the switch S is closed, when the switch S is now closed, the charge flows between the capacitors for some time until you get equilibrium. So now what are we going to do? We are going to close this switch. We are going to close this switch. So it's going to look like that. So remember, this had charge Q, right? And some charge is going to now flow. It is going to go that way. How much charge? Let us say small q. Let us say small q flows out like that. So now this will become Q minus Q. And that will become Q. That will become Q. Clear? Now C1 is 6 microfarad. So 6 microfarad. Let me write that here. 6 microfarad. And C2 is 12 microfarad. Notice that. That is 12 microfarad. Okay. So charge small q flows from here to there. Now what are the charges Q1 and Q2 on the capacitors C1 and C2 at equilibrium? Q1 is capital Q minus small q. Q2 is small q. Basically that is the answer. Of course we don't know what is small q. Capital Q we know it is 30 microcoulomb. So our job is to find small q. So how do we do that? How do we do that? There are two ways. We can say that the potential drop here is equal to the potential drop there. So Q minus Q by 6 microfarad must be equal to small q by 12 microfarad. So that is going to, both of them are going to be equal to V. I will show you how to do that. And then later I will also show you how we can solve the same problem using equivalent capacitance. Okay. So let us say that the potential drop is V. So you can say V, the potential drop, final potential drop. This is the initial state. No, this is the final state. So final potential drop is Q minus Q divided by 6. Now Q, capital Q is 30 micro. So I'm going to write 30 micro minus small q by 6 microfarad, right? Q minus Q by C1. Remember Q equal to CV. So Q divided by C will give you V. But this V you can also say is equal to this V, which is Q by 12 micro. Small q by 12 micro. And if I solve this, I'll be able to find small q, right? You have micro, micro, etc., which you can cancel. So let me do that. So if I cancel this micro with that micro, 6, 12, you can basically say cancels out, gives us factor 2. Cross multiply, 60 micro minus 2q, 60 micro minus 2q equal to q. So 3q equal to 60 micro. So q is equal to 60 micro by 3, 60 by 3 micro coulomb, right? Everything is SI units, so coulombs, right? This micro comes in here itself. So it is 20 micro coulomb. Is this the answer to the question? No, this is the charge that flows. So then what will be Q1? Q1, this is Q1, this is Q2. Oh, Q2 is equal to 20 microcoulomb. So this is Q2. I can write Q2 here. But what is Q1? Q1 is capital Q minus small q. The charge on C1 is Q1, final charge, right? What is capital Q? 30. 30 minus 20. So 30 minus 20 will give us 10 microcoulomb. So this is Q1. This is Q2. So 10 and 20 microcoulomb. Q1 is 10. This one says Q1 is 20. So this is wrong. This is Q1 is 10. This says Q1 is 15. That is wrong. Q1 is 30. That is wrong. Right? So Q1 is 10. Q2 is 20. This is correct. This is correct. So the correct answer is option C. Q1 is 10 microcoulomb. Q2 is 20 microcoulomb. So this is one way of solving. This is one way of solving, right? So this is a good way of solving where we are not using any big formulas. But I could have also said the total charge is capital Q, which I already know. Total charge is capital Q, which I already know. By the way, if I now use the fact that small q is 20, I could have substituted that here and got V. I could have found out that V is 20 divided by 12. They have not asked us, but we could have done that. 20 microcoulomb divided by 12, we could have found out that V has to be 20 microcoulomb by 12 micro. Right? 12 microfarad. And then if I cancel this, 4 into 5, 4 into 3, 4 into 5, 4 into 3. So you will get that the final potential drop is 5 by 3 volts. So V is 5 by 3. So V across C1, let's say, or C2, okay, is 5 by 3 volts. This is what we got. Right? That was not asked, but that's what we got if we actually substitute. If I had decided that let me use formulas, which also is a good way to solve, okay, which is also a good way to solve, then you can say total charge here is capital Q, equivalent capacitance is 6 plus 12, okay, equivalent capacitance, C1 plus C2. Why? Because they are in parallel, same potential drop, they are in parallel. So 6 plus 12, 18 microfarad. So then we can say V, the final potential drop, must be total charge divided by the actual capacitance, equivalent capacitance. Total charge is 30 microcoulomb divided by 18 microfarad. Now 6 into 3, 6 into 5, so 5 by 3 volts. Hey, that's what we got here. But here we got it in one step. One step we managed to get that the final potential drop is 5 by 3 volts. But that is not the question. No problem. Once you know the final potential drop is 5 by 3 volts, C into V will give you the charge. So now you can say Q1 is C1 into, let me call this V final, V final. What is C1? 6 micro into 5 by 3 volts. 6 by 3 is 2, 2 into 5, 10, 10 microcoulomb. Is that correct? Yeah, that's correct. Now, what about this charge, Q2? Same potential drop. So, it will be C2 into V, C2 into V, C2 into V final. What is C2? 12. So, 12 microfarad. So, always remember that farad is the SI unit. So, I am not writing farad, but micro is not SI unit. No, you have to put the micro there. So, 12 micro into, what is this potential drop? VF. Oh, 5 by 3, 5 by 3 volts. 12 by 3, 4, 4 into 5, 20. So, this is going to give me 20 microcoulomb. Isn't this the answer? Yes, we got it like this by writing an equation, but you can also use the formula that the net capacitance, once you connect them like this, is C1 plus C2, that is the effective capacitance, and the total charge, because the charge can't go anywhere. Once you connect it like this charge can redistribute, but if you take them together, right, if you think of the equivalent capacitance, this plate and that plate is like one big plate. And so the charge will be capital Q, which we already know, 30. So using the 30 microcoulomb divided by the equivalent capacitance, you get the potential drop across the equivalent capacitance, which is actually this potential drop, that potential drop, same thing. And then using that you can find Q1 and Q2. So this is one approach, this is another approach. Both are very useful. Do whichever one you are comfortable with. Let us now look at this question that appeared in JEE in 2019. In this figure that is shown, after the switch S is turned from position A to position B, so I have shown it in position A here and in position B there. Okay, basically this switch is going to be turned from A to B. Find the energy dissipated in the circuit. Not when it is connected here. When it is connected and this capacitor is getting charged, C is getting charged, even there will be some amount of dissipation, but we are not talking about that. Basically, after it has been turned from A to B, how much is the heat dissipated or energy dissipated? That is the question. Well, right now, this is going to get a charge Q. How much would be the charge? C into E. C into E. But I'm not interested in this. I'm going to say U initial. What is the energy initial? You know the formula for the energy stored in a capacitor. How much is it? Half CV square or Q square by 2C. If this is Q, and anyway all the answers are looking at Q square, right, by C kind of form. So Q square by 2C. So the energy stored in this capacitor, that doesn't have any energy, right? It is no charge there. So Q square by 2C. There are many different ways to solve this problem. I'm going to show you the shortest way of solving it. I don't even need E. This battery is going to charge this capacitor. There is going to be a charge capital Q and the energy stored will be Q square by 2C. When you flip it over, when you lift it out, it will still be Q. When you connect it like that, this will end up having Q minus Q, right? A charge small q will travel out like that. And so this is going to end up with small q. Now you can say, I want this energy, I want that energy, and do that. Or you can say, wait a minute, these two capacitors totally, what is C effective? It is 4C because they are in parallel. And for that effective capacitance, what is the charge? Well, the charge is conserved. No, you can't have the charge. It's only going from here to there. But overall charge is capital Q. So what is the total charge? Capital Q. So what will be the total final energy? U final. Well, it is going to be Q square by 2 times C effective. So Q square by 2 times C effective is 4C. Right? Q square by 8C. So I know the initial energy, I know the final energy. What are we talking about? Energy dissipated. So obviously the initial energy minus final energy, that is the energy lost. What do you mean by lost? Energy is never lost. That is the energy that is dissipated as heat. So energy dissipated, which is basically heat. Heat is the energy dissipated. And so this must be U initial minus U final. And so this minus this, Q square by 2C is common, I'll remove it. Q square by 2C into 1 minus 1 by 4. 1 minus 1 by 4 is 3 by 4. So 3 by 4 into 1 by 2 is 3 by 8. So Q square 3 by 8 and Q square by C, right? So 3Q square by 8C. 3Q square by 8C, that is this option. So the answer to this question is 3 by 8 Q square by C. Okay, that is the energy that is dissipated as heat. That is the energy that is dissipated as heat. Here, of course, I use the formula that C effective is C1 plus C2, which basically means C plus 3C, 4C. But suppose I didn't want to use that formula. No problem. You can talk about this energy, you can talk about that energy, and you can add it up. You could have also written U final is this energy plus that energy. What is this energy? Q minus Q by, right, Q minus Q whole square by 2C plus small q square by 2 times 3C. small q square by 2 times 3c. But I don't know what is small q. That you have to find by saying small q travels that way. This potential drop is equal to this potential drop. And if you do this, you will be able to find out what this potential drop is. You can do all that, find small q. We've already seen that. And then using that, if you substitute, you will find that this will give you exactly this answer. But obviously, this is so much easier, no? Because once you realize that these two are in parallel, then you say, oh, total charge is capital Q and the effective capacitance is 4C. So that means the energy is stored using the formula. No, it is effectively this capacitance. So therefore, it must be Q square by 2 times 4C. And that gives you the answer very, very, very quickly. If you do it like this is not enough. No, you can't solve it yet. So what do you have to do? You have to find out small q. How will I find out small q? You can say this potential drop equal to that potential drop, which I'll show you. Q minus q by c, right? This is the potential drop, final potential drop, is also equal to q by 3c. This potential drop equal to that potential drop. So if you cancel the c, cross multiply, you can find out what small q is by solving this. Take that and substitute that, and finally you will realize that you will get the same answer. I suggest you try it out and make sure that you get this answer. That way you will know that both of these are actually the same approach. Let us now look at this question that appeared in JEE in 2018. A capacitor C1, which is 1 microfarad. Okay, so this capacitor is 1 microfarad. Is connected initially to this battery, which has voltage 60 volts. So if this is 60 volts, this will be 60 volts. So you're going to get a charge Q here. How much will Q be? Q equal to C1 into this potential drop. So 1 microfarad into 60 volt. So 1 into 60 is of course 60. So you're going to get 60 microcoulomb. So that will be the charge on this plate, right? That is the initial state. Now C1 is disconnected from the battery and connected to a circuit consisting of C2 and C3, consisting of two uncharged capacitors, C2 3 microfarad, C3 6 microfarad. So this is how much? 3 microfarad, and this is 6 microfarad. But they are in series. They are in series, right? So if I actually try and combine them together, can't I figure out what will be the equivalent capacitance? Now there is a formula, right? Capacitors in series, 1 by C2 plus 1 by C3 will be 1 by C dash. Suppose I call it C dash, 1 by C dash. You can do that, or you can write C dash is C2 into C3 by C2 plus C3. Now this is a better formula to remember, easier to do. You just multiply these two. So then I can write C dash is 3 into 6 by 3 plus 6. 3 into 6 by 3 plus 6. Now 3 plus 6 is 9, 3 into 6 is 18, 18 by 9 is 2. 2 microfarad. 2 microfarad. So the equivalent capacitance for this C dash is 2 microfarad. Now that makes things easy, because you see this is 1 microfarad and that is together 2 microfarads. And when you take this switch and you flip it that way, then this is in parallel, not with C2, not with C3, but in parallel with C dash. So if you take this whole thing together, what is C effective? Or we can call it C equivalent. What is it? C1 plus C dash. C1 plus C dash. Which is how much? 1 plus 2, 3 microfarad. So we know the effective capacitance. But you see, this had capital Q, 60 microcoulomb. Now part of the charge will go that way. Part of the charge will go like that, which will go and land up here. So it is going and landing up here, Q. But remember, whatever comes there is also going to come here, because these two are in series, right? You're going to get minus Q here and you're going to get plus Q there. So you're going to get the same charge here. So C2 and C3 will both have the same charge. Find the final charges on C2 and C3, both have the same charge, small q. And what will happen here? You will get Q minus Q. Q minus Q, right? You originally had capital Q, now you have Q minus Q. Now you can solve this by saying this potential drop must be equal to that potential drop and all that. You can do that, right? Or we can say, wait. I know this potential drop because you think of this as one single equivalent capacitance. What will be the charge on that equivalent capacitance? Q minus Q, right? This is the plate that you're going to see. If you see it from there, Q minus Q, small q, when you add, what do you get? Capital Q. So the total charge is capital Q. And at the bottom, you will get minus Q, minus capital Q. Okay, so capital Q. Okay, so what will be the potential drop across this? So final, if I say V final, okay, if I basically put it this way, V final, what will be V final? That is easy. V final, you can either say Q minus Q by C1, small q by C dash, you can do that, or you don't need to because you have C equivalent. You can write Q divided by C equivalent because the total charge is capital Q. Now capital Q is 60 microcoulomb and C equivalent is 3 microfarad. And so what do you get? Micro cancels, you get 20 volts. 20 volts. So this is the final potential drop. Now with this I can find what is this charge, I can find what is that charge. Now this charge, the question doesn't ask that. But let us anyway find it. What will be this charge? This charge will be V final into C1. So if I call that Q1, which is capital Q minus small q, right? How much is this charge? C1 into Vf. C1 into Vf. What is C1? C1 is 1 microfarad, Vf is 20. So 1 into 20 is 20 microcoulomb. This question did not ask us that. Let me just put a border around this. This is Q1. This is this charge, Q1. Q2 and Q3, they are equal to Q. So let me write that Q2 equal to Q3 is equal to Q. And how much will this be? Can I say it is C2 into V? No, because this Vf is across C2 and C3 together. So this Vf is across C dash. So you have to say Vf into C dash. Okay, so C dash Vf. Here I can say C1 Vf because this Vf is across C1. Whereas here this Vf is going to split between C2 and C3. We don't know what the split is, but we know for C dash it is Vf. Okay, C dash we know, right? What is C dash? 2 micro. 2 micro. And what is Vf? 20 volts. So what do I get? 40 microcoulomb. So what is Q2 and Q3? 40 microcoulomb. Does that make sense? This is 40 and this is 20. Okay, together it has to be 60. Charge is conserved. Good, we are safe. And the answer that we want is Q2 and Q3, right? The charge on C2 and C3. So the answer is 40 microcoulomb. This is the answer expected. But I'll tell you something interesting. Actual question, they had made a mistake. Instead of saying find the final charges on C2 and C3, they had written, the actual question in JEE had written find the sum of the final charges on C2 and C3. But if you say sum of, then you have to say Q plus Q, 40 plus 40, which is going to be 80. It doesn't make any sense, right? Why will you add up these two charges, right? So it doesn't make any sense. And 80 was not an option given. So the question had a mistake. But what they really meant, and then you look at the solution that they provided, the JEE provided, right? The actual expectation was they're talking about the final charges on C2 and C3, which is 40 microcoulomb. So this charge, Q2 is 40 microcoulomb, C3, they are in series, so they must have the same charge. So Q3 is also 40 microcoulomb. So I hope you have understood how to solve this question, right? So the basic idea here is if you basically combine this and convert it into a single capacitance, and then you say, okay, these two can also be combined into the equivalent capacitance. The charge that goes from here to there, you don't have to worry because it's still on this side of the equivalent capacitance. When you say think of this as equivalent capacitance, you're thinking of a big plate, which includes this plate and that plate, right? Think of it like that. So these two plates, similarly, you're thinking together. So basically this is C equivalent, and this is Q minus Q, and this is Q. So effectively, what is it? Q. So Q, C equivalent, and therefore you can use that approach to quickly solve a question like this. We are now out of time, and so I'm going to ask you to do this question as homework. This is very similar to the questions that we have done. Okay, so basically initially this capacitance C1 is connected to a battery, the battery is removed, and then it is connected to new capacitor C2, and when the switch is closed, they're asking a question about it, the amount of charge on capacitor C2 once equilibrium has reached, right? Very straightforward, the same approach that we have used so far, you can use that to solve this question. Please do this as homework, then you will understand that what you have learned now really works, and you can use it for question after question after question that comes up in the JEE based on capacitors. Of course, we have only looked at one type of question on capacitors. There are many, many more. So I have prepared an entire micro course on capacitors. You can get this from the AhaGuru Courses app. You can download the AhaGuru Courses app from Google Play Store if you have an Android phone or a tablet, or you can get it on the web by going to ahaguru.com/microcourses, and do use this code YT YouTube, right? YT15, and that will give you an additional 15% discount. So you will then see this capacitor course. It has 5 skill builders, 107 concepts and solved examples explaining every type of question. Starting from the basics, you will find that you will be able to become super thorough with any kind of question based on capacitors and capacitor circuits. Switches questions, yes, but also a lot more with dielectrics and everything else. So I strongly recommend that you take this course. You will find that suddenly your understanding of capacitors, ability to solve problems dramatically shoots up, and you will be able to solve every question that comes up in JEE, NEET, as well as your board exams. All the best. If you like this video, please hit the subscribe button below. And if you have some comments, or if you have doubts in physics or math, please write it in the comment section. I will take one of your questions and make my next video. See you all in the next video soon.